we understand that taking up average of a complete cycle or any number of cycle is not a good idea. The math turns out to be 0. One another way is something called as root mean square. You guys have to know that root mean square itself is a method, and that method is picked up and applied over here. So root mean square per se is applied wherever you have varying quantities. So you want to figure out mean in ways. So the best way to do is root mean square for time varying or any varying quantity. The steps looks like this. So say we have set of values, say A, B, C, and so on and so forth. Say there are n such values, n values in total. Now, what the method tells is, first thing is you square them, right? And then that's why the square, and then find the mean. Mean of what? The square itself. So how do you find the mean? Add all the values, divide with the total number of values n. That will give you the mean of squares, and then take the root. So I'll call it as, say, some value m. So take it as root of m. So basically root of this entire expression. This gives us root mean square of that set of values. That's all. Okay. So by default, when we square things, everything will be positive, and that's how the conversation continues. Agree, guys? Now, this method of root mean square, we are applying it to AC. So this is given the name root mean square of AC, virtual value of AC, effective value of AC. So all those names are synonym. So let's look at the official definition of root mean square of an AC. It's something but it's equal to the direct current, which produces the same heat that is produced by one complete cycle when we pass an alternative current through the same resistor. So basically, we're looking from the point of view of energy. And then we are talking about finding the average. That's the discussion, right? That's how I started off the discussion with. I started off the discussion by telling that, you know what, let's look at in terms of energy. If we talk in terms of energy, one complete cycle does produce some energy, does produce some heat. Is it not? Just because they're moving back and forth does not mean that they are not doing any work over there. They can do work. So to figure that out, average is not a good idea, and we are looking at alternative. It's denoted by IRMS, IV, and I effective. Now let's relate. Let's find the IRMS and relate it to I naught. To do that, we are starting off with taking up AC source, passing through the resistor R, and we are looking at a small amount of heat for a small duration of time. So dH is what we are looking at. So let's recall one thing. I'm using something new over here. Let's recall heat. Heat is given by what? This is one of our formula. Then if I substitute P, we have this formula. Okay, let's make use of this, right? That makes sense. So dH will be equal to, here the instantaneous value is I naught sine omega t the whole square r into small time dt, right? That makes sense. So for one complete cycle, how will we be able to find the entire heat? Just integrate from 0 to h. That's it. As simple as that. Next. Not sorry, 0 to h, 0 to t. When I substitute this, I naught square is constant, sine square omega r is constant, dt. So basically, I need to handle this. So sine square theta is given by, how do you integrate this? By now you guys should be used to this. Yes, we have to make use of 1 minus cos 2 theta by 2. So your h will turn out to be I naught square is constant, r is constant, divided by 2 is constant, Then integration from 0 to t, open the brackets, 1 minus cos 2 not theta, here it's omega t. Then we have dt. Next, we have I square r by 2. So integration of this will be t minus sine 2 omega t by 2 omega, integrated from 0 to t. So when I do substitute, I'll end up with by 2 t minus sine 2 omega capital T divided by 2 omega. And when we talk about 0, when we substitute 0, 0 minus 0 and all of that, we'll end up with no value over there. So let me make it as 0 itself. Again, this has to do with integration. If you guys are not comfortable, then you have to do integration and come back. So you should not, physics teacher should not be explaining this over here. Okay, so don't make your physics teacher sit and explain all of this. Learn the basic and then apply. So we have 2 omega t, which is nothing but 2 into 2 pi f into t. So these two are inverse of each other. So they end up with 4 pi. What is sine 4 pi? Yes, this is nothing but 0. So we end up with the heat generated by this source is given to be this. Now, we define IRMS to be a heat which is equal to the current into time RT, right? So one complete cycle for this amount of current passing through this resistance, this is the amount of heat being generated. This is as per the definition, right? That's the whole definition. Now, we have an expression 1 and 2. They're talking about the same heat. So from 1 and 2, what can I tell? I can equate them. So we need to relate IRMS with I naught, so we can equate them. So RT is common, and therefore IRMS is equal to, if I take the square root and both ends, this will become I naught root of 2. So this is your final expression. So 1 by root 2 is what? 1 by, where is the root? Root of 2. Oh, 2 root. Okay, should be this. Root 2 is 1.414, but 1 by root 2. Oh, yeah. Okay. 0.7. So this is 0.71 I naught. So it's 70% of your peak value. Okay, so that's your root mean square of AC. So we'll understand it a bit more. I don't want to put more pressure on this particular video. So we'll just sticking to getting introduced to the idea of root mean square. Itself is a method. It goes through this process if you have a data to find the mean. And that we are applying it on AC. So root mean square of a AC is defined as the heat that is equivalent to a DC current, which is, which is producing the same heat and all of that. So based on the definition of heat, right, basically we're going back to the idea of energy, because in terms of values, we can't compare DC and AC. When we try to take the normal average, things are going haphazard, like 0 and all of that, which is not true. They are doing some work, and that work we can figure it out with the help of heat. So when we do that math, we'll end up with this particular answer.